Hi everyone, and welcome again. In this video, I want to go over exact equations. And let's just go over the definition first, and I'll go over the details, and I'll do a couple of examples so you know how they work. So now, what is a definition of an exact equation? A differential expression, m of x by dx plus n of x by dy, is an exact differential in a region R of xy plane if corresponds to the differential of some function f of xy defined in R. First order differential equation of the form m of x by dx plus n of x by dy equals to 0 is said to be exact if the expression on the left side is an exact differential. So let's see what that means. Now, before we go into details, let's take a look at this note. If you take this equation and divide everything by dx, every single term, then dx is canceled here. You're left with mxy plus nxy dy dx equals to 0, 0 divided by dx is dx. Then dy dx, we know we can write that as y prime. So sometimes if you see this, that's also an exact equation. So, well, when I say exact, we'll see, but both notations are the same, that and that. So you see this notation, you can just change it to dy dx and write it like that. Now let's understand this function f of xy first. F of xy, you can call that is a function of two variables with continuous first partial derivatives in a region R of xy plane. Then from calculus, the derivative of z equals to f of xy is also known the total differential. So please remember that the total differential of f of xy, you can say that's dz, is df dx, the partial of f with respect to x times dx plus the partial of f with respect to y times dy. And one thing I want you to just notice right now here, df dx is m of xy and df dy is n of xy. Just notice that because this is going to help you when you solve an equation like this. Now, there are some cases that this function equals to a constant. So when you write the total differential, then that becomes 0. So this expression becomes 0. So, and let me read that for you. In other words, given one parameter family of functions f of xy equals to z, we can generate a first order differential equation by computing the differential of both sides of the equality. For example, let's take this example. So when we have this expression equals to a constant. Now, if I calculate, if I say this is f of xy, so that expression, if I calculate the partial of this expression with respect to x, let's just take a look at this. It's going to be 2x minus 5y. That's what we have here. So df dx and times dx. The partial of this expression with respect to y, you know, this is going to be 0 because x considered a constant when there's no y. And it's going to be negative 5x plus 3y squared, negative 5x plus 3y squared times dy. And that equals to the derivative of a constant is 0. So, and that's our function. Now let's see how we can solve some equations. Before I go to the next one, I went over some other notes here and I want to share that with you, then we can do some examples. So now if you have this differential equation, we saw this expression m of xy dx plus n of xy dy equals to 0, or you know now if I write it like that, m of xy plus n of xy y prime equals to 0 is exact in a region R in the xy plane if the left side of the equation is the differential of some function f of x, y. We saw that. I'm just repeating myself, but there's nothing wrong with that. Now, if that's a constant, then the total differential, remember, that should be equal to 0. Now, whenever you're given an equation, you have to test for exactness. That means the partial of m with respect to y should be equal to the partial of n with respect to x, or simply dm dy equals to dn dx. If this is satisfied, then you can say it's an exact equation. Now let's go over the procedures of solving the equation, and we're going to solve one so you see how that works. Solve the following equation for f of x, y. How do you do that? You use this, guys. We set that df dx is m of x, y, or you can say df dy equals to n of x, y. So you use number 1 and number 2 to solve for f of x, y. Steps. So you are going to be given an equation like this. That's the equation. Step number 1, check for exactness, because not all the time they're exact. So you take the partial of m with respect to y, and you take the partial of n with respect to x, and they have to be equal to each other. Or again, this is the Leibniz notation, different type of notation, but they mean the same thing. Step number 2, if it's exact, then you can use these to solve for f of x. So I think let's take a look at this example, and that's going to make a lot of sense. So we are given this equation, 2xy dx plus x squared minus 1 dy equals to 0. What I do, I always determine what m of xy is and n of xy. So this is our m of xy, which is 2xy, and this is our n of xy, which is x squared minus 1. And as I told you, the first step is to check for exactness. So you take the partial of m with respect to y, and I put both notations for you. That's the partial of the derivative with respect to y of this expression. That's just 2x, because x is a constant. Then you take the partial of n with respect to x. Again, this is the same notation, and these are not true, these are just the partial. Or the partial of this expression with respect to x, and that's also 2x. And we know 1 equals to 2, so it checks, therefore is exact. Little note when you see these 3 points, time is therefore in mathematics. Step number 2, we're going to solve for f of xy by using these two. And note f of xy equals to c. So we're going to pick, sometimes it's easier to pick number 1, or sometimes it's easier to pick number 2, depending on the expression, which one is easier to integrate. So please remember that note. Here, so I pick number 1. The partial of f with respect to x is equal to m xy, and we know m of xy was 2xy, so we have it here. So then to solve for f of x, just take the integral of both sides. So what you need to know, that's an integral with respect to x, of course, so you get x squared plus y plus g of y. What is that? That's just the constant of regular integration, but it could be a function of y, because the derivative of this function with respect to x will be 0. If you have one variable, we just put c for regular integration. That's the constant of integration. But in this case, it's going to be a function of y. And our goal is to see what that is. So number 2, we're going to use this df dy equals to n of xy. But what you need to do is just take the derivative of f with respect to y. We have our f of xy here. So if I do that, we're going to get the derivative of x squared y is going to give you x squared, because again, x squared is a constant, and the derivative of g of y, we don't know what g of y is, we can just write g prime of y. And we know that equals to n of xy, and n of xy, let me show it, and we have that here. So we can put that equal to n of xy, substitute the expression by x squared minus 1, because that's n of xy, and x squares cancel. So you know g prime of y equals to -1. But what we want is g of y, and that's pretty straightforward because we can take the integral of both sides and we get g of y equals to -y. Little note here, no constant needed because the final solution will have a constant. So here you don't have to put plus c because we are going to have a constant in the final solution. So we have our f of xy. Now equals to c. That function is x squared plus y plus g of y. And we found g of y to be -y. So you say x squared y minus y equals to c, substitute. Or you can, in this case, that's the implicit solution, but you can easily isolate y here and you get y equals to c over x squared minus 1. You can give some numbers for c and graph it and see those curves. And I put here, this is the explicit solution. Now, little notes, let me go back to, there's some examples, you can look at them, they're solved for you in detail, and they all work the same way. So this is not a bad example. I'm going to go over this fast so you can see. So if you are given the expression like this and you have an initial value here. So, well, I put the general solution here, but let's see how this works. So what you can do is cross multiply. If you cross multiply, then you get cosine x sine x minus xy squared times dx. And then that times that. So it's y times 1 minus x squared dy equals to 0. Check for exactness. So I did that fast here for you. So it is exact. Please redo that and see if you get -2xy. Then here you can start, instead of putting df dx equals to m of x of this one, because that's probably hard to integrate, you can just say df dy equals to n of x, so y times 1 minus x squared. Then here it's easier to find f of x y. You get y squared times 1 minus x squared plus the constant here is a function of x, not of y. So then then you can write df dx equals to you take the derivative of this function, and that should be equal to m of x now. So you put them equal, and h prime of x, if you isolate, so these two cancel, you're left with cosine x cosine x. So, and what you need to do is take the integral of this. Remember from calculus, you can use substitution, or if you see it, you can do it fast, but I did show it here for you. Couple of ways to do that. If you write cosine x sine x dx, you can do substitution. U is sine x and du is cosine x dx. If you substitute, you get u du, and the integral is 1/2 u squared plus c, and you can u is sine, so you substitute, that's what you get. Or you can change sine squared to 1 minus cosine squared, and you get 1/2 minus 1/2 cosine squared plus c. But notice 1/2 is a constant, so you can just take these two and write the constant, make it one constant. So I can say this is probably the capital C. So this constant here is the sum of that plus that, which is still a constant. And please get used to those in an integration. When you see a number with the constant, they change it to another constant, just remember because they're both constant. Another way of solving this, you can say u equals to cosine x and du is negative sine x dx. So you can take the negative sign out and put u du, and the answer is going to be negative 1/2 u squared plus c. So here, but what is u? U is cosine x. So basically we end up with the same answer. Here you didn't need a constant, but this is just to refresh your memories of calculus too. How to solve trigonometric, how to evaluate trigonometric integrations. Now the rest of the examples, take a look at them. They're very similar, and I will solve more examples in the next videos when I do the homework. Thank you for watching, and I'll see you all in my next video, or you will see me in the next video. Have a great day, everyone.